Hey, everybody ready? Ready to go? Okay. So remember what we were doing? We were talking. I think we finished up with the proof of Taylor's theorem, right? And to give you an idea, the main idea of the proof is like this. You express your function using Cauchy's formula. So remember the setting, right? You have there's some point z naught, and your function is analytic on some disk around z naught, and you're trying to show that there's a power series expansion around z naught in that disk, right? So you pick some z there, and then you use Cauchy's formula to get an expression. You take some slightly larger disk here, and you're going to integrate that. So that's what we call K1. Right. So you use Cauchy's integral formula, and then the main thing was to basically sneak in the z naught, right? So you have this term, this 1 over zeta minus z, and you pull a trick, which is to recognize that this is the same thing as summation z minus z naught to the n over zeta minus z naught to the n plus 1 from n equals 0 to infinity. So this was the trick, right? And we accomplished it by noticing that. He said, well, look, this is the same thing as zeta minus z naught minus z minus z naught. And so you sneaked in the z naught, right? And you factored out 1 over zeta minus z naught. You got 1 minus z minus z naught over zeta minus z naught, right? And then you said, well, this thing here is the expression for a geometric series, right? This is the sum of a geometric series as long as this thing in absolute value is less than 1, right? And so, which is okay because we're integrating our zeta minus z naught is on this ring, which is the distance of zeta to z naught is greater than the distance of z to z naught. Right? So we do have that, the size of that is less than 1. Right? And so you say, okay, so we're going to express this then as the summation of z minus z naught, z minus z naught to the n from 0 to infinity. Right? And that gives us the sum that I had raised earlier. Right? It gives you this zeta minus z naught minus 1. Right? And so you sneak that, you take this thing and then you sneak in the z naught, right? You sneak in the z naught, right? And then what you have is Cauchy's integral formula, right? Cauchy's integral formula for derivatives of f at z naught, right? And that gives you times powers of z minus z naught to the n, right? And so that gives you the Taylor series expansion, right? So that's the trick, right? You take the Cauchy integral formula, and then you sneak in your z naught, right? Sneak in your z naught with this infinite series, and then you realize that again we and then use Cauchy's integral formula for derivatives to get back the power series expansion about z. So just to remember the idea of the proof of Taylor's theorem, because today we'll do something we'll basically play this trick in a slightly in an inverted manner to get the so-called Laurent series. Okay, everyone awake? Yeah, I'm smiling because of a sort of a crazy memory. I'm not going to tell this story right now, but so some of you who've been in my class before may have heard me tell the story of the person who stalked me and believed that she was a vampire, et cetera, about 10 years ago or so, 10, 11 years ago. Anyway, at one point, this clearly insane woman said that, made some comment to me about the way I pronounce the word Laurent series. Anyway. Sorry. You say, the way you say Laurent series is very unusual. No, it's not. No, it's not. It's just how you pronounce it. Okay. Yeah, it's a long story, and probably best told near Halloween. Okay, so Taylor expansion, right? Right, so let's just recall it. F analytic in a domain, and Z naught some point in the domain, then f of z equals summation the nth derivative of f evaluated as z naught over n factorial z minus c naught to the n when n equals 0 to infinity in the largest disk around z naught in B. So you have any really the way we should say this is that any holomorphic function is actually an analytic function. Right? Actually has a power series expansion about each point in its domain. Okay, so we're going to take a little bit of a detour and talk about zeros. Yes.
Same power series being convergent.
Say it again.
Is the power series convergent on the same?
Yes. So this power series is valid in the largest disk around Z naught.
Right.
Am I not understanding?
No, I just looked at my notes and never mind, I get it.
Okay.
Yeah.
Okay, so we're going to talk about zeros and analytic functions. It's kind of like a dull topic, but it'll have actually a pretty interesting result about it. So start off with the following definition. If F is analytic at Z naught, if f of z naught is equal to 0, okay, and the first derivative at f of z naught, the first derivative at z naught is 0, and up to the n minus 1th derivative at z naught, if all of those are equal to 0, and the mth derivative at z naught is non-zero, then we call, we say f has a 0 of order m at z naught. Okay, so we think about what this means in terms of the power series, right? So in terms of the power series expansion about Z naught, right? You know that the power series expansion looks like this, from 0 to infinity, right? And so what this is saying is that right, the first m terms of the power series are 0, right? The first m terms of the power series are 0, right? And that the first m coefficients of the power series is 0, and that the m plus 1th coefficient is non-zero. Right? That's if you want to translate it to what it means in terms of the power series. So in terms of the power series expansion, this means that coefficients the first m coefficients are 0, and the m plus 1 coefficient is non-zero. Where we're using Ci to denote the ith coefficient. I just wrote what we said. Okay, so you have some sense of what it means to have a 0. Another way that people characterize this is the following. Say F is analytic. Z naught. F has a 0 of order and Z naught. If and only if f equals z minus z naught to the n times some function g, where g is analytic and g z naught is non-zero. Right. Does that make sense? That should make sense, given what you have, given what we just said about the Taylor series expansion, right? Right. You know, if f has a 0 of order m, right, f has a 0 of order m. That means that f of z equals summation z sub n z minus z naught to the n, where the first m coefficients are 0, right? And it's 0 infinity, but the first m terms are 0. In other words, you could write, you just factor out z to the m, right? So, right, this thing starts from m onwards, right? This goes from this thing starts from n, and then it goes onwards. Right? So you can factor out z minus z naught to the m. And what do you have left over? Well, you've got this you just factor out, right? This thing starts with the z minus z naught to the m power, And so let's just factor it out, right? And then you have a power series that starts from the 0th power and goes onwards, right? It should be completely clear. Right? Michael, are you right? Yeah. Okay. Good. Okay. So so what do you do? Well, this is of course it's going to be your G, right? So let this be let this be G to 0. And you see that this function this is going to converge in the same it converges in the same radius as this, right? As in the same radius as f, right? And you see that for g of z naught, right? G of z naught is going to be c sub m, which is non-zero. We're basically almost saying exactly the same thing here. And then going backwards, the same thing, right? If you know that f is something like this times an analytic function, right? And you want to see that f has a 0 of order m in z naught. Well, you just take the power series of g, and then you multiply it by the uniqueness of power series. Then that's going to be a power series that will be your power series for f, right? And then you look at it and you say, oh, this thing has the first m coefficients are 0, and that's the end. Okay, so backwards is even easier. Right? You say if f equals this. G is analytic. Then G is some power series, right? D sub n minus c from 0 to infinity. So G sub n z minus d naught to the n plus n from n equals 0 to infinity is the power series expansion for f about z naught. Right. And you see that the first m coefficients are 0 and the m plus 1 coefficient is non-zero. Okay. So nothing going. Okay. Any questions? Should be pretty. We haven't done anything. Okay. Does anyone want to ask a question? Yes, I'm not waiting.
I was searching for a question, but I was not clear how we got the uniqueness of the Taylor series.
Oh, well, that's because the coefficient turns out to be the nth derivative at that point over n factorial.
Since we have a formula for that.
Yeah. So it has to be that, right? No matter what you do, that's what it's going to be. So they all do the same. When I first came here to apply for this position, they asked me to teach a class, and I asked a question, and I stood here for like 30 seconds or something. And apparently, like all the teachers in the classroom were like, "Why is he waiting so long? He's waiting so long for them to answer." But I think if you wait long enough, somebody will ask a question. There's a sort of like a. I thought it was strange for me to wait so long.
Did somebody answer?
I don't remember. I remember that the lecture was on the chain rule. Yeah, I think no, actually. Okay, so maybe I'll have you do an exercise. This is a corollary. Something for you to think about for a few minutes. Suppose f is analytic at 0. If f of z0 is 0, but f is not identically 0 in any neighborhood of z0, then there exists a punctured neighborhood and epsilon of z0, with z excluding z0 itself, in which f, let's see, define 0. Okay. Yes.
Remind me what it means to say that f is not identical to 0.
So f is not. There's no neighborhood where f is 0 constantly. Yeah. F is not a. There's no neighborhood where f is constantly equal to 0.
What is the purpose of identically there? What is that clarifying?
Somebody might say, do you mean that if f vanishes at one point there? Right. That's not what I mean. I mean there's no neighborhood where f is always 0. Right. I'm not saying there's no neighborhood where f is touches 0. You just say, you know that f has a 0. That 0 is going to be of some order, right? Either the function is 0 everywhere, or the 0 is going to be order m. Right? Either you have a 0 of infinite order, in which case the function is just a 0 function, right? Or that thing is going to be of order m. So yeah. So we actually don't need this part to say say that. So are we, what's wrong with our thinking, or what's wrong with my thinking? So what you said, home, and maybe it's just because I tend to go along with whatever other people say. So what you said was that, well, look, if f is constantly equal to 0 in any neighborhood, of z0, so in a single neighborhood of z0, then f prime of z0 is going to be equal to 0. Yeah. Right.
So can you make that if f is identical to 0 in some neighborhood, then
in some neighborhood,
if and only if work, because if you have the derivative equal to 0, then you have, like, you're then approaching at every direction, the derivatives, the limit is 0. So then,
are you saying that whenever the derivative is 0, the function's bound to be
oh wait, no.
0 in the whole neighborhood? No.
Oh.
Something's wrong with that logic, I think, right?
So we can't go in the other direction, so we can't say that, because our supposition is if f of z not is z. Oh, okay. If you take the contrapositive of that, it's f prime of z not equal to 0 implies f is not identical to 0 in any neighborhood. But that's not the direction that we want. So we don't know that the 0 is order m. I mean, we don't know that the 0 is order m.
Okay. No, that's all right. That's all right. I should be sane enough to catch such a thing. But, sorry. Okay. In any case, we don't need to do it. So we just say, look, f has a 0 of order m. Then f is gonna look like this. This thing is non-zero at z0. This thing is non-zero away from z0, right? And we can find a neighborhood in which this thing is non-zero. We know that outside of the center, this thing is also non-zero there, and so that's the end. So, so this is a statement of what's called the isolation of zeros. Right, that if you have a zero, either the function is identically zero in some neighborhood of that function neighborhood of that point, or there's a function neighborhood in which the function is never zero. So your zero is isolated, or it's completely zero. There's a neighborhood in which the function is identically zero. So another way of saying this is the following: if f is analytic on a domain D and Z0 a 0 of f. If for all r greater than 0, the punctured neighborhood around Z0 contains a 0. Then f must be identically equal to 0 on D. Okay, well, this is not actually a rephrasal, but a sort of a strengthening or a consequence of the previous one. Okay, so what we're saying is that you have this point, right? You have this point, and there's the function is 0 there. Okay, and further, you're making the assumption. Suppose that for every radius, there is a point, right? There's some point where the function is 0. Okay. So I can take another radius. There's going to be another place where the function is 0. No matter what radius I take, there's always these points where the function is 0. In other words, what we're saying is that this 0 is an so-called accumulation point of the set of zeros. Okay, that this thing is actually a limit point of a sequence of zeros. Okay. It's actually the limit of a sequence of zeros. In that case, then the previous theorem applies, right? The previous theorem will say that your function, your function is your function must be identically equal to 0, right, in some neighborhood, right? So by the previous there exists a neighborhood in which f is constantly equal to 0. Right? Because what the previous thing said was that your zeros are either isolated or they are, in a complete neighborhood of zeros, right? And what we have here, suppose you have a 0 that's not isolated, right? Since it's not isolated, there must be some neighborhood. There must be some neighborhood where the function is constantly equal to 0. Okay, everyone follow? Okay. So there must be some neighborhood in which the function is equal to 0. Okay. And what we're saying is that, in fact, that forces the function to be 0 on the entire domain. Okay. Why is that? Why is that? You have this point 0, and you have a neighborhood. You have a neighborhood on which the function is equal to 0. Well, you could say, should I let you think about it? I'll let you think about it. Yeah. Say how would you Michael? Yeah.
Well, then the radius contains another 0 point, and so can't you recenter f around the new 0?
Yes.
And then basically extend it and walk around.
So you can sort of walk around, right?
Yeah.
So to make that a bit more formal, what you need to say is what was the name of that lemma? The path covering lemma? Path covering lemma. Yeah. So you say, well, and take any other point, and take any other point and then draw a path to it, right? Well, one thing we know also is that if we take the power series, that the power series expansion for f around z0 is valid in the greatest disk contained in the domain, right? So in fact, we know that the function is 0 all the way here because we know that all the derivatives are 0 here, and so our power series expansion tells us the thing is actually 0 in this greatest disk around centered at 0. Right? Is that okay, Michael?
Yeah.
Yes. Okay. Right. Okay. And then you say, well, by the path covering lemma, we know that there's a sequence of disks that are contained. Right. There's a sequence of disks. This picture is a little wrong. But you tolerate it. There's a sequence of disks that all of the same radius so that the disk covers the center of the next disk and the previous disk, which is where I pictured this one. In any case, covers at least the center of the next disk, right? And so you know, and contained inside of your domain, right? And so you say, okay, well then this thing is contained in there, and so the derivatives there are also 0, right? And thus inside this maximal disk, right, which must contain the disk from the path covering lemma, and so on and so forth. You just keep on going from one center to the next center and going onwards to the other. And so that would by argument similar to the proof of the maximum modulus principle, you know that f of z1 equals 0 for any z1 in your disk also. And so your function must be 0 everywhere. Yes, Rebecca?
Sorry, could you walk through the logic of the first step of the proof, how it comes from that?
Yeah. So the previous statement was this isolation of zeros statement, saying that given any 0, it's either an isolated 0, right? Either there's a neighborhood in which that's the only 0, right? There's a punctured neighborhood in which the function is never equal to 0, right? So either that happens, or there's some neighborhood in which the function is always equal to 0. Right? So either your zeros are isolated zeros, or they occur with a whole neighborhood of zeros. Right? Okay. So now here's the setup. In the second one, you have the following setup. You have a 0, and in every neighborhood, there's another 0. It's a non-isolated 0. Being a non-isolated 0 means that there must be some neighborhood in which everybody is zeros. The zeros are either, they either stay by themselves or there's a whole neighborhood of them. Okay, so there's a whole neighborhood of them, and then you can use the path current lemma to just bootstrap your way over to any point in the domain. Yes, Michael.
You say that the R's don't have to be the same. They're not going to be the same. Are they?
In the path current lemma, they are the same.
They do.
They are in the path current lemma. They are the same. And the good thing is that you know, so here's the domain. The good thing is that so you know that so here's what the path current lemma says. If you have a z naught and you have a z1, right, then there is a sequence. There's a sequence of subdivisions of this thing, and a fixed radius. So that these disks all lie inside of the domain, and each disk contains the predecessor and the successor. Okay, right. That's what path current lemma says.
But in this case, depending on your path, the one closest to the boundary is going to fix your R.
Yes, that's right. That's right.
And so I guess would you choose an R at the first and then choose your path dependent on that, or would you choose your path?
No. It's the other way around. You have the path first, and then the path covering lemma tells you that there's an R that works throughout.
Gotcha.
Yeah. And so the thing is that if you look at, you do your path current lemma thing, and then you say, well, I know that for this first disk is contained inside the biggest disk that works the biggest disk around Z naught that is contained inside your domain, and you know that the power series expansion for it is 0 there, right? So that means that you know that the disk that came from your path coming lemma is the function is identically 0 there, right? So that means that point two is within the set of zero of the within the place where the function is all 0. Okay, and you say, okay, well then let's take the power series expansion about that point. Right? The power series expansion shows me that the function is 0. In fact, in the greatest disk possible around that point, which contains the row disk from the distance lemma, from the path current lemma, right? And then you just keep on going. Right? So you can, it's possible to get to the next disk. It's possible to get to the next disk and see that the function is going to be 0 in that disk as well.
Would you not just choose an R of the radius of the smallest disk that contains of the power, the smallest disk around a point that's contained in a function along the path? Or does that make sense?
So
as you R.
So I think what you're saying is that, well, you know that the function is 0 here.
Yeah.
Right. And so so you know that the power series expansion about the second point will show that your function is 0 in some neighborhood. Right?
Yes.
How do you know that it will be this whole neighborhood? How do you know it will be the whole neighborhood? The whole row neighborhood, where rho is the radius that you got from the path current lemma. Well, the reason you know is because the power series expansion is valid in the maximal case, right, which is going to be bigger than rho.
I mean, this is not important anymore. We're fine.
Okay. Well, is it actually clear, or are you just trying to get out?
It's clear. I mean,
Yeah.
I guess I'm misunderstanding my question.
Okay.
So I know that it's identically 0 within the power series.
Yes.
The full disk.
Yeah.
Around each point, which is contained in the domain. So if you want a radius without the radius, for each successive point, to move from each successive point, when your subdivision is kind of like the number of subdivisions is kind of arbitrary, right? Depending on your, I mean, both dependent on the R you choose, like the subdivision of the path.
That the subdivision as well as the R come from the path governing law.
Yeah, so that then when, for like a valid R, can't you just choose the radius of the smallest disk? The smallest disk. I guess never mind. Sorry, I'm working backwards anyway.
Okay.
I just figured it out.
Okay. Okay. So I hope this is clear. This is sort of interesting, right? If you have, notice what this says, right? If you have 1, 0 in your domain that's not isolated, right? You have 1, 0 in your domain that is an accumulation point of zeros, then your function is 0 on the entire domain. Your function is 0 on the entire domain, right? Okay. So what does that give you? Right? That gives you that right, if you have two functions, f and g, analytic on some domain, and if the set of points where f of z equals g of z has an accumulation point, then what?
Then the functions are equal.
Then the functions are equal. Right? Then f and g are equal on the whole domain. Right? And so this is a really bizarre sort of thing for analytic functions, right? Differentiable functions, complex differentiable functions, right? You have a once differentiable and thus infinitely differentiable function. As long as the points of agreement, right? As long as, if you look on the plane, like if you look in your domain and you find that there's one place where the zeros accumulate. The places where the functions are equal to each other accumulate, right? Then they have to be equal everywhere. This is sort of like saying, if I have 1, 1/2, 1/3, 1/4, 1/5, blah blah blah. I have the sequence of points on the real line, right? And I have two functions, f and g, and they happen to have the same values on all of these, on all of the 1/n. So for all the natural numbers, and they're just once differentiable. Then they have to be equal for all time. They're equal. Those functions must be equal for the entire real line. Right? That would be the analogous statement for real value functions. And you see how crazy that is. That's nowhere near true for real value functions. Yeah. Christian.
For this corollary, you also need that this accumulation point is in that set, right?
Yeah. Yes. Yeah. But the set is open. The set is open, right? D is an open connected set. Okay. Right. So no, you're right. Sorry.
Or, well, what I was trying to say was that, so the proof of this is going to involve you taking f of z minus g of z equaling 0.
Yeah.
But so for this to work, you need to have that the 0 itself, one of the zeros itself is a accumulation point of zeros. But over here, it seems like you're saying any accumulation point.
Yeah, so if So how do I phrase it? If f, I'm gonna just take a cheat one. If f minus z has a 0 b such that every neighborhood contains a 0. Right? I think it should be able to, one should be able to say that, let me think about how to say that one properly, but for now, let me just write it this way. But in any case, I hope you see that this is sort of an astonishing statement.
Doesn't really feel that astonishing. Because like Taylor series basically says that the value of your z naught plus the derivative determines everything in that area, right? So it seems like it would make sense that
So,
right?
yeah, maybe not. Yeah, maybe not. So certainly, if you said you have two analytic functions, right? Certainly, if you have two analytic functions on the real line, and you know that their expansion is valid on the entire line, and you know that those expansions, and you know that, say, they agree on some tiny segment that contains the origin, then you know that that's true as well. So maybe it's not that astonishing. But I guess so. Maybe the astonishing thing is simply that that once differentiable implies infinitely differentiable. Okay. Okay. So now we're going to get to this thing called Laurent expressions. So the setting is the following. You have some function f, which is, say f is analytic in an annulus. Centered at some point z naught. So you have some point z naught, and you have some annulus around that thing. So radius r here, radius capital R, and you know that the function is analytic on the annulus, but maybe it's not analytic on the inside, and it's not analytic on the outside. Then, for any z in the annulus, it turns out that f of z can be expressed as a power series plus a power series in z minus z naught and a power series in 1 over z minus z naught. So people usually just write this as f of z equals summation from negative infinity to positive infinity. But what they mean is that it's the sum of these two power series. Because with this one, you're not really sure where you start, right? Where do you start? From negative infinity and start counting? Good luck. So you have this double power series, and this thing is called the series is called the Laurent series of F around Z naught in the annulus A. So it will, the series will depend, of course, on Z naught, but it will also depend on the annulus. So if you choose a different annulus, then you get a different expression. So if you choose the annulus, that lies outside this annulus, you get something different. We'll see some examples. Okay, so. Okay, where, I should say, where a sub n is 1 over 2 pi I, integral f of zeta minus c naught to the n plus 1 zeta over some circle of radiuses, some circle of radius rho about z naught, where circle of radius rho about z naught, where rho is between r and r. Okay, so it doesn't matter what rho you choose. It just has to be some. You choose some path that lies inside the annulus, and you integrate over it, and you get the coefficients for all n. So I think there's no way we're going to make it through. There's no way we're going to make it through this in 4 minutes. But let me try and give you an idea of how it works. Okay. So the idea is this: you have your annulus, right? R, little r, right? And you have your point A, your point Z that lies inside there. Okay. And what you do is you choose 2 circles that bound that Z, okay? And let's call the outer guy C1. So this outer circle is C1, and it's a radius rho 1, and then the inner guy is C2, a radius rho 2. Okay. So then you use Cauchy's integral formula. Use Cauchy's integral formula, and you say, well, my z lies inside here, and what I'm going to do is I'm going to make a cut here, and I'm going to consider the integral over this thing this way, and like this, right? I'm going to use Cauchy's integral formula on that path. Going up here, backwards in this direction, and then down, right? And you see that Cauchy's integral formula will say that you get the integral over the outside guy minus the integral over the inside guy, right? So you get the integral over the outside guy minus the integral over the inside guy. That's the zeta minus the zeta, right? So I'm going to separate that. C1 zeta minus C2 Okay, and then what you do is you basically play the trick that we used for Taylor's theorem twice. So you say, well, look, on this first one, on C1, right? I'm integrating on C1. So what I'm going to do is I'm going to express 1 over zeta minus z as, again, I'm going to sneak in the z naught, right? I get 1 over 1 minus z naught over zeta minus z naught. Right? And you see that this thing converges because z minus z naught, right? Z minus z naught, I'm sorry, z minus z naught is strictly smaller than zeta minus z naught, right? Because we're on the bigger zeta, zeta is now on the bigger ring, right? And so you get your, by the same trick, right? You get z minus z naught, zeta minus z naught, and this one, right? Okay, and from there you basically get that. Putting that back in here gives you basically the positive terms. It works out just like the Taylor expansion. Okay, but you can't do that on the other ring, right? You can't do that because this doesn't converge there, right? This doesn't converge there, and so you just play the corresponding algebraic trick, which is to say that you say, well, let's express it like this: 1 over, negative 1 over z minus z naught, 1 over 1 minus zeta minus z naught over z minus z naught. So you express it in the opposite way, where this is over that, right? Which is what you want because now you're on the smaller ring, right? And then this converges, right? So you get negative summation zeta minus z naught un over z minus z naught plus 1. Right? And this gives you the negative terms. Okay. So it's basically just a clever understanding, a good understanding of the proof of Taylor's formula, of Taylor's theorem gives you Laurent's theorem. Okay. Okay, so that's what we'll do next time. I have one set of homework that has been sitting in my office for a little while. Sorry. Yeah, and don't forget, we have an exam next week sometime, right? A week from Thursday, I believe.
Professor, it would be awesome to take that Wednesday night. I haven't even thought about that. But,
Yeah.
what time Wednesday will be? Or should I email you? Is that easier?
Basically any time before 6.
Okay.
As long
Sounds
as,
like-
so, it's an
It's like
hour
an
and
hour
a
15.
half, hour 15, so as long as you finish before 6,
1 o'clock work?
that would be fine.
Okay,
Yes.
great. Just come to your office.
Yes.
Cool, thank you.
Did you get back the last exam?
Yes, but I'm afraid I don't have it with me. It's in my office.
Can I come see?
Yes, but not right now. Yeah, not right now because I need to run to my next class.
Professor,
Yes.
if you need to go to your office, then I can come back for this, but,
No, I think it's a quick signature or something.
well, it needs my current grade, so it's in your office.
Yeah. Just put your exam grade on.
Okay.
Yeah.
Okay, then I do need your quick signature.
Okay.
Do you have a pen? Because I don't have a pencil.
So this is the transfer.
Yeah, it's like a midterm report thing. Thank you so much for your.
Oh, no. That would be great.
We'll see.
Where do I set my?
No, don't go.
I would only be going across the street. Thank you.
When's the deadline?
Like next Wednesday. I just have to, I mean, it's gonna be mailed across the street, so
Can you just like hand it to my
I might just walk it over.
Better get used to this anyway.
Yeah.
Used to what?
Walking to mud. No, I guess not walking to mud. Could be living.
Professor, you said you're gonna teach 131 in spring of next year, right?
Well, that's sort of up in the air. I would like to, but other people also would like to teach different courses, and there's some argument, there's some debate about what we're going to do next year.
Whatever happened with the 2-3 or 2-2 class meeting vote?
That's still being discussed.
Yeah.
Yeah. So they've asked us to put down an actual plan to which we're committed. What we would do, what would your department do if we moved to a sort of transitional, like some people are on 2-2 and some people are on 2-3, alternating. What kind of concrete plan would you have? And then what would you do ultimately if we switch to a 2-2? So yeah, so it looks like it's happening, if not immediately, but it's happening. Yeah. Although well, I guess it wouldn't be